Hello scholars, welcome back. Mr. Hinkle here. In this lecture, let's talk about a key topic in physical oceanography, ocean temperature. So we will analyze ocean temperature by vertical structure and discuss the components of its variability. Ocean temperature. So temperature is going to be the amount of thermal energy in seawater. We know temperature as how hot it is outside or how cold it is outside. And that is a measurement of how much thermal energy that is existing within a medium. When we're talking about weather, the medium is air. When we're talking about the ocean, the medium is going to be seawater. The average temperature of the ocean is about 4 degrees Celsius, which that's pretty cold. Now, that's because the oceans are so big. If we think about land, continental margin, deep ocean basin, mid-ocean ridge, we'll do it back over here. Cool, I just did our marine provinces. It's because most of the ocean is deep. And if you remember from our discussion on light, please see that light only goes around 1 kilometer deep in the ocean. So this is going to create an extreme variability with depth. Now, the range of temperature is about -2 degrees in areas that are very salty, where the high salinity lowers the freezing temperature of water, allowing liquid water to be present at -2 degrees, all the way up to 30 degrees in some tropical equatorial regions, so 28 to 86. Earth's temperature, or the ocean's temperature that is important for regulating Earth's climate, driving ocean currents, and supporting life. So this is the big take-home for physical oceanography, is the key aspects of physical oceanography support life on Earth through helping regulate or buffer Earth's climate. How do we measure it? Well, you can drop a thermometer in the water and record it and get a point sample, but we can't do that a million times all at once to get constant data. If we want continuous data, like for many things that we measure in the ocean and on our Earth, we use satellites. The Visible Infrared Imaging Radiometer Suite, VIRS, measures infrared radiation given off to create global observations of land, atmosphere, cryosphere, and ocean. Basically, it's measuring the temperature of our entire Earth everywhere, and we can pull that data in to get a continuous sample of what is our ocean sea surface temperature. This gives us a structure. So we can understand the sea surface temperatures, right, from satellites, but we've got buoys and instruments that go into the water that help us get into depth. And what we find is a structure that goes like this. There's the mixed layer, where temperature is relatively constant. And then a sharp, let's go green here, a sharp decline with depth. And then near constant. This sharp decline with depth is called the thermocline. I hope you can see this lime green. I'm not sure, but I'm going to write over this just in case. Gives it kind of a fun effect. Up here is the mixed layer, and then down here we have the deep ocean. The deep ocean is where we have this near constant temperature at around average of 4 degrees Celsius. The mixed layer is going to be near the surface, mixed. Think this is where the wind is blowing, the air-sea interaction is happening at that boundary between air and water, and you have waves that are causing it to mix, and then a rapid decline with depth from about 200, 0 meters, 200 meters, 1,000 meters. this is a structure that we'll see over and over again. We'll see it in light, we'll see it in salinity, we'll see it in temperature, in density. The thermocline is the rapid decline in temperature with depth. There's a lot going on here, but I love figures and the information that they can convey and help us go from a theoretical model into actual recorded observations. So if we look here on the right side, this is going to be our scale. And this is potential temperature. Reds, deep reds, 25 to 15. Greens are about 8 to 5. Purple, like blue to purple, are around 4 degrees. So purple to blue to green up here. So from the deep ocean, 6,000 meters, all the way up to 1,000 meters, it goes basically 2 degrees to about 7 degrees. And then from 1,000 meters up to the surface, it goes from 7 degrees up to 28 degrees. So this is the thermocline right here. And then it's kind of relatively constant up here. It's kind of, given the precision of this, that you kind of lose the mixed layer. But you can see from 1,000 meters up to the surface, you go from 7 to 25. That's this part of the graph. A rapid decrease in temperature with depth that then gets cooler as you go down, but the average temperature of all the oceans, because of the volume of the ocean, is right around 4 degrees. Cool. So one way that temperature varies in the oceans is by depth. It's hotter at the surface, it's colder at the bottom. Okay, we're done here. Let's go home. Just kidding. If we want to think about the deep ocean, there's little temperature change because it's away from the primary heat source, which is the sun, giving it thermal stability. And in these regions, temperatures may fluctuate by less than half a degree. There's no light that reaches the deep ocean. There are deep ocean currents, but they exist in distinct water masses. We'll see that in ocean circulation. That creates boundaries and barriers within deep water that gives it a pretty stable temperature. Okay. Another factor affecting ocean temperature is going to be latitude. So we can think of this as it's hot at the equator and it's cold at the poles. Intuitively, I think we know this. We have these images of the North Pole and South Pole. Brr, they're so cold. We have these images of hanging out on the beach in the tropics and our board shorts and whatever, and just like enjoying swimming in the water because the water is warm at the equator. We've also got seasonal variability, where it's hotter in the summer and cooler in the winter. So latitude, season. What else do we got? Ocean currents. Europe is warmed by the Gulf Stream, which is the most famous of all ocean currents, because the Gulf Stream essentially brings warm water from the equator across the Atlantic Ocean to northern Europe, creating pockets of warm water that are warmer than the surrounding area. So currents are responsible for the redistribution of heat around the world, causing areas to be warmer and cooler than others. We've got higher salinity, lowering the freezing point of seawater. So salinity is on average about 3.5% or 35 parts per thousand within the oceans, but there is variability there also because nothing is always just the average. There's nuances and variability within everything. Same thing with salinity. The salinity is going to affect the temperature. And then the last thing is going to be atmospheric conditions, which is basically saying Is there a big storm that's blocking out the sun? And if there is, then that light doesn't make its way to the surface, and it's going to cause differences and changes in the amount of heat exchange. So let's zoom out. Temperature in the oceans is directly connected to temperature in the atmosphere, which impacts temperature on land, which causes our global climate to be affected. It's important that 71% of Earth's surface is covered by oceans because of water's high heat capacity. Oceans absorb a lot of heat, and then ocean currents distribute a lot of heat. And there are significant changes in ocean temperature that cause episodic variability in weather patterns that we experience on the west coast of the United States. And pretty much it's the west coast of North and South America, called El Nino and La Nina. This is a really cool thing. See my videos on El Nino and La Nina special weather to learn more about how and why that actually happens. I guess I don't have a slide in here, but now that I'm talking about it, I probably should, so I'll just talk about it. If ocean temperature has a global effect on climate, then that directly relates to the habitability of land and sea, thereby influencing, supporting organisms, terrestrial ecosystems, marine ecosystems that allow life to exist. And ultimately, we could say, thank you because we are here, thanks to our oceans and their ability to help regulate climate by the way that they moderate temperature on our planet. Thank you so much. It's been great. We'll see you in the next one.